Okay, I think it's time to get started with the question session of our two speakers from this morning. Who would like to pose the first question? Not all at the same time. Yeah, Robert.
Bianca, you mentioned that you have, in the continuum, you have some additional degrees of freedom that are however massive, right?
To the length matrix.
So my question is whether you can interpret those as having anything to do with torsion.
Yeah, so I do believe. Sorry.
You can't say much about degrees of freedom.
So actually for a long time I interpreted these degrees of freedom as torsion. And in one version one sees it if one uses this modified Plebanski approach. I need to remember. One has to derive this action, one has to solve for the connection. But for some reason, there's two ways in which one can kind of interpret the connection. And one, because there are two frames one can build, two different frames. So say one is a B field, but then there's another choice where you dress the B fields with something in addition. And then one choice, the connection you get is kind of as torsion, but is metric. And in the other choice, it's torsion free, but non-metric. You know, I have to, well, kind of, it's more details in the calculation, but we haven't, I think it's not really published yet, so I would need to look into calculations. And so you get this torsion degrees of freedom if you look into kind of the connection picture. And you could, well, in the area metric picture, it's kind of area metric, but if you look in the connection picture, it seems at least there's one interpretation where these are torsion degrees of freedom. 5 plus 5. Well, in the area metric, you have 5 plus 5. Yeah, so I'm not sure whether it's the most how many torsion degrees of freedom do we have? 6 times 4, 24. Yeah. So it might be some subclass. Yeah.
How do you get these masses? Where do they come from?
Well, I presented two calculations. So one on the lattice. I'm not sure where they come from. They come out from the calculation. Well, calculational wise, you define your lattice action and on a regular lattice, it's important to take a regular lattice because in the end you want to define a lattice Fourier transform. And then once you have your action or your Hessian, depending on these lattice momenta, you can set them all to 0. The lattice momenta. That more or less defines you the matrix of masses. And then it's actually rather generic that you get lots of non-vanishing eigenvalues, and it's non-generic that you find null eigenvalues. And in fact, but you do get these 10 massless degrees of freedom, which correspond to the length matrix. So that is certainly something non-generic, which comes from kind of the form of the action. But everything else comes with these masses. So, and yeah, I mean, this comes from the area Recce action, and that these are kind of, well, it's not very, well, it's completely non-obvious if you see the action where these masses come from. In the modified Plebanski approach, it's rather obvious because I mentioned, well, in principle, you have to impose these constraints, but you replace these constraints with a potential. And the potential, well, more or less, it's m squared something quadratic in the B field. So or in these constraints. And so what you constrain is indeed like these extra degrees of freedom. So you give them a mass explicitly.
Because you put in the potential.
You put in the potential, yeah. I mean, or, well, the idea is to replace the delta function, which you can see as an infinite potential, by a smoother potential.
So this is very much it perfectly matches what you expect from effective field theory, where in the presence of torsion, if you consider terms of dimension 2, which are the dominant ones at low energy, you will only have the square of torsion. So it's just massive, and the equation of motion says that it is zero.
Yeah, no, I mean, for a long time, we interpret the fact that we didn't impose these constraints as torsion degrees of freedom, so it's only recently that it can be interpreted as area metric. So before that, I would have told you these are torsion degrees of freedom. So.
But if you don't have a potential, can you move the mass as you like, or they are fixed?
In this modified Plebanski approach is a choice. So in the lattice approach, it comes out of the calculation. Yeah. So I wouldn't know how. Well, you can also add additional terms in these constraints, but for the area redshift part, there's a very natural geometric action, and it comes as a result. And for the modified Plebanski, as I said, it's a choice. And then you would say, well, since you expect via this weak quantization, that there are fluctuations away from the length metric, but these should be basically Planck scale suppressed. So you would expect these masses to be on the order of Planck mass. But otherwise, you can kind of adjust it to anything you want, or into those higher powers. So it's not very clear. I mean, you would go like in effective field theory to start with a quadratic term.
Any follow-up on that? Hello? Yeah.
No,
Yeah, I don't see any follow-up, so please go ahead.
so another question to be honest. Sorry, Paulo. You didn't give us many clues. You didn't leave many questions open. So, Bianca, so of course you said, before you embarked on this perturbative expansions, well, I'm assuming that, well, it will give me maybe interesting information about the quantum regime. Of course, what we see, when we put kind of what we think is just GR on the lattice, like it's between, is of course informing the path integral and taking a continuum limit. These two things simply do not commute. And all the interesting stuff comes from them not commuting. So is there anything in that particular formulation that should believe us that it might be different?
Well, I agree that it's a highly non-trivial question whether this assumption is kind of justified. And I did work towards kind of trying to realize that, but as you know, it's a highly non-trivial problem. Here we can debate: is it better, or is it in this case more helpful to have more variables? And we did some investigations in simpler models of the phase diagram using tensor network method, like in 2 dimensions, analog systems, and 3 dimensions. And this at least included always a phase where, well, at least the curvature was 0. So that was a curvature of which would correspond to the full SO4 curvature. And I defined also a state which would be the BF vacuum. So in we know that there are different phases. It could be that perturbing around this phase, around BF vacuum, where curvature is 0, might give you this result. I think that's actually what is done in lattice Young-Mills. Yeah. Yeah, no.
But wonders where is instances also like
That it's non-renormalizable. Yeah.
to area variables.
Yeah, as I mentioned, I don't think that that the action we get is a UV completion. It just captures this extension and like it does not capture at all that areas are discrete and so on. And obeys this non-linear constraints. So there are many effects which are not captured. So there, yeah, I mean we could. What we started is to again use the fact that we have a bit more structure than say in causal dynamical triangulations to look at symmetry reduced things where we can do the path integrals with a finite number of variables. Of course, you would still say, okay, that is not sufficient for the continuum limit, but you try to add more and more variables to see how things go and behave. So that is kind of the
the spinful models SAR, I mean, not effective spinful models.
yeah.
Yes, you said, well, there will never anything interesting can be computed in those.
I didn't say that explicitly because somebody will shoot me for that, but so I do think it's very, very hard, and I'm not sure when that will be happening. I have also to say there are not too many people working on this. It's not the most attractive thing to do, to fight with that.
But then going to the effective model,
But
reduces it by again a large factor.
It reduces.
It's kind of
No. It reduces this by a large factor, but we still have the problem that it's. Well, that as far as I know, even for I don't know what you would Ising model, that as far as I know, nobody has calculated the Ising model in 4 dimensions in a real-time approach. But I think there's progress because like tensor network methods have been applied in 4 dimensions to the Ising model. So I don't know. It could be that in 20 years we could do that, yeah.
Last question. So would you have some kind of more CDT-inspired way of treating the geometric, what's mixed in with your spin assignments? That you're, rather than letting those vary, you
some over
connectivity.
Well, I mean, in this aspect, they are kind of possibly two very different approaches. There could be one thing which so far I only know that it works in the Euclidean. If you go to the Euclidean, introduce a cosmological constant, you replace the flat simplices with homogeneously curved simplices. And if you are Euclidean, it's a sphere, and so you have a cutoff on your spin. And well, if you make your cosmological constant very large, you get a very small cutoff. So then you could go to a limit where your size is either 1 or 0, and then you have to interpret like 0 as redefining, that defines rather your connectivity. And that could be a limit. I'm not sure it's useful. That could be. Yeah. So it's kind of related to the fuzzy sphere quantization. But then also you introduce automatically a very strong cosmological constant into your action. So that could be one thing. So that is, well, also in the Euclidean, that spin 0 would correspond to having no edge and defining somehow a different connectivity. in the Lorentzian, again, well, first of all, spin zero means that possibly there is something that's null. And also, I'm a bit confused. I mean, it's not necessarily a cutoff that you have there, but other people actually claim there is a cutoff. So I have not yet understood these claims. Yeah. So, yeah, you could possibly see these approaches where you have more variables or something is already kind of more effective than just working with a combinatorial structure. But yeah.
That's a really good for converting this away from linear.
Yeah, no, I agree. So I think the advantage of having these more variables is that you can do these things which however rely on these assumptions, and the disadvantage is well, you would have to sum over all these variables, which I think is an interesting challenge, but it actually is a challenge in a lot of areas, I believe.
So
Can I do?
Systems to demonstrate,
So I mentioned that we develop these tensor network methods, and so far in 3D and in 2D, and we had analog models. Not 2D gravity because BF or these, it's trivial. So the action is just proportional to the total area. So we had to come up with different toy models, which we called spin nets, and that's where we explored the phase diagram.
standard 2D.
No, it's not. We cannot compare it to Liouville gravity. I mean, we know that we got phase transitions and so on in these systems, and the constructions we claim is kind of similar to these constraint constructions, and so that's why I believe that there are phase transitions. But of course, you can say, oh, this is 4 dimensions, very different from 2 dimensions, and so on. So,
Any follow up on that?
It was.
Ivano?
The new point.
Yeah.
So if this has been already addressed, I apologize, but what do you expect regarding the non-linear effective action? Like GR plus subleading or something else?
Yeah, I mean, I would hope it's a non-linear completion what I wrote down. I mean, that's the first GR plus y squared. And I guess I could come with, if you have the length metric, well, we have the area metric, but possibly, but part of that is a length metric. The only diff invariant action up to certain orders is GR. And then again, also to nonlinear order, I mean, one can try to compute it in this approximation I have done. I think at some point I tried, but that was a long time. I tried to do something different to higher order. Just that, I think for good reason, nobody does higher order perturbation theory on the lattice. I would, it's a bit of question whether why should be interesting. But in the continuum, I would rely more on kind of the arguments of diffeomorphism invariance, which indeed give you only a restricted number of possibilities.
I'm wondering in particular about the couplings of these negative kinetic energy. I was wondering in the full nonlinear effective action, they could lead to.
Yeah, so this is indeed a very interesting question. So at quadratic order, we found this is fine-tuned to decouple, which is indeed rather non-trivial because generically you would get something unstable if you couple positive harmonic oscillator to negative harmonic oscillator. And well, I didn't mention it so far, but if you ask me, area matrix kind of in the number of terms you can write down, it seems to be rather a nightmare. But it might be possible that this is a very restricting criterion which restricts you very much, that you keep your stable dynamics. Yeah, but we haven't tried, so and possibly, I mean, Kirill was actually first very negative about these negative modes. Then he heard a talk by John Donahue. Then he was much more positive. So, yeah, and before he was saying, "Oh, that's excluded now," but I don't know. It seems to be also that there is no conclusive arguments to allow them or not to allow them. But yeah, if you take the positive spin on that, they could help you to restrict the many possibilities you have in area metric gravity to write down couplings.
Yeah, I just wanted to ask because you mentioned some RG work, so you must have a suggestion from the effective action already in work.
Well, yeah, we wrote down some higher order terms. Yeah. And as you know, you take always very peculiar truncations. That's what we did, And well, and in particular, we looked only at potential terms, So no, not so far. I mean, yeah. So we could. I mean, first, well, it was marked that we setting up to compute the beta functions, and now we want to explore these special points. So the special it's a particular point in the quadratic coupling space.
So just to follow up, I mean, Kirill in the old days had, I don't know, conjecture, but I don't know to what extent he put that in.
It's very normal.
Yeah, that's a sector that's closed,
Yeah.
subset. It's closed.
The normalization flow. I don't know if I think the status was that he tried to find people which would compute that, and he never found someone. I'm not sure what the status was. Also, I think it was never confirmed and maybe excluded. I don't know. I have not asked him explicitly.
What was puzzled me about that is when he formulated his MBT, or he said, well, I have one relative family that goes through GR, whereas since there are general arguments that it's that, I mean, I don't know, it's not the gamma because you have a one over action.
No, he had the chiral, yeah.
It is not GR.
Yeah, I don't know exactly what he meant with. I mean, he had the chiral version, so which means you do not have a gamma. You have 15 degrees of freedom, so you have only chi plus or something.
Some parameter, so if you
maybe it's a mass or so. Well, maybe it's. Yeah, maybe it was something like the mass. If you send the mass to infinity, you do get GR. Right, maybe he called it 1 over m or something. I don't know. Or he put a coupling in. Or in the coupling in front, you couple H menu to this extra field. If you put that to, you provide, yeah. Anyway.
But having those sector under normalization, that would be also the new vision for what
my vision.
In the space of all possible actions you could write down for these variables.
Not necessarily. I mean, as I said, also that the action does only capture certain aspects of the spin forms. So, I mean, I would agree that you have to do renormalization, but I would do that. So far, I did try that with the full lattice models, as crazy as it is. But maybe we see that in the. Well, I'm sure that we will. One thing is to compute this functional renormalization flow. And then the potential is only, the potential terms would be like the mass terms. But I believe we will have also running in, for instance, gamma, well, which Kirill just didn't have really as a parameter. So, yeah. So I don't know. I don't want to speculate about that.
So you're allowing the m plus and minus to be different and see if they converge in some parts of the flow, or you're setting them to be the same?
Well, in general, they can be different. Well, I have to check with Mark whether he has had them different or not. I think he might have done that for simplification, because otherwise we have, I don't know, 5 couplings or 10 couplings. So it's, as you know, if you have 5 couplings, it's yeah, that's why you consider only 2 couplings. So, I mean, then to find, I mean, and there's not there's a priori, we don't really know where to look for interesting fixed points and so on. So it's a bit different from, I don't know, coupling gravity to matter. It's a new system. So
You're looking at zeros in a high dimensional space.
yeah, so yeah, and this is and this is already with quite truncated. So as I said, if you consider higher terms with second order or higher derivatives, so to answer Renate, they will in general all run. You might ask what is the relevant coupling. But I don't believe it will be just the potential. You will also get this higher derivative terms.
Okay, any more follow-ups? I think John was first and then Smarty.
I have a question for Paulo. I find it amazing how this amplitude method is able to reproduce the results of classical GR. But in your amplitude, you also have H-bar effects. And but I presume you're not calculating all the diagrams that give H-bar effects. For example, like vacuum polarization, you don't bother calculating and it's of order H-bar.
No.
How, given your technology, how hard would it be to include all the extra diagrams that also require H-bar, and then get the classical quantum corrections out, the higher orders also?
I mean, you compute the amplitude, so you have everything there.
Right. So it just means you have to put in a few more diagrams into your amplitude, because things like the vacuum polarization only give H-bar effects.
Yes,
And there's a couple others that I know of.
yes.
If you put those in, is it much harder to do for you? I mean, the way I did it was painful, but maybe.
I mean, at one loop, that's what I was trying to do to reproduce your result. And I'm still a bit confused, but should be able to get the amplitude, get the classical and the quantum amplitude, and extract what the number that you say.
And then at higher orders, it becomes harder and harder.
And that can be done also too. I mean, at each order, the same.
Okay, you're good. Impressive.
Maybe I can quickly follow up on that. Do you have any idea at which order the post-Minkowski is of the same order as the first quantum correction?
I mean, we exclude quantum. I mean, quantum. I don't know how to answer this question.
The quantum is very much smaller than any post-Newtonian at any order that they're ever going to calculate. It's basically the classical scales like GM over R, and the quantum scales like G over R squared. And so M is always big. And so they're never going to be equal.
Follow up? Okay.
So, as you said, of course, the same computation we perform just in classical GR without bothering about amplitude. So, Are there really cases in which amplitudes make computation simpler, or not? Because from your perspective, why people should use scattering methods instead of just classical GR technique?
I mean, a two-loop, that's the only way that amplitude has been computed.
Sure, but in GR you do not speak of amplitudes and loops, you just do a computation through, I don't know, maybe Lamour does some Hamiltonians and without involving basically really amplitude techniques.
I mean,
What is the gain?
the two things can be put together. The advantage of the amplitude is that you don't get an expansion in velocity. You get the complete relativistic expression. Instead, what people have done, they compute up to a certain Pn, a certain V over C order. And that's what all the literature of, Blanchet, Damour, and company. Now, the post-Minkowskian is an expansion in which you don't expand in velocity. You expand in power of the Newton constant, G. So at a certain order in G, you get all the expression.
I guess even in classical GR, you can do some post-Minkowskian expansion without.
And I'm not aware that people have done that.
One of the advantage amplitudes against value.
Yes.
It's important. Because if you do the brute force computation in GR for whatever, singling out the gauge artifacts is a huge problem. Amplitudes against invariant by construction, so you get whatever which doesn't depend on the have in mind for each.
I mean, to make an example, you do one PM, and then I've computed the iconal, which is an integral in 2 dimensions. But instead, you can compute the potential, which is an integral in 3 dimensions. And you get 1 over R. But you get 1 over R plus velocity correction. So the first term is 1 over R, then you get 1 over R, V squared, V to the 4th, a certain power. And that all come together.
So your point is that if you want to do some post-Minkowskian expansion, the amplitude method is more suitable in this sense.
Yes.
Any more? Is a follow-up?
Yeah, just a follow-up. But also, I think it should be emphasized that we had 30 years of doing the general relativistic calculation, and these guys caught up in 2 years, 3 years. So it's clearly, and they've moved ahead by doing the post-Minkowski. So it's clearly a technique that's amazingly powerful compared to just doing post-Newtonian expansion of GR.
Sort of related, again, the fact that you've got these, it's related back to the comment that there earlier. Maybe that contains the answer. The question is really in terms of these observables, which you say are observables for gravity, which are based on scattering, and the perturbations. So, first question is, are they strictly diffeomorphism invariant? Because we know that if we think of diffeomorphism invariant quantities and trying to define observables, this becomes a big issue in sort of continuum quantum gravity. Are these a class of these perturbative observables that are diffeom invariant that you're constructing? And what about observables that we expect, in the non-perturbative regime, where even for black hole spacetimes or something that are not perturbations about flat spacetime? Where would, so just to understand whether these are in fact observables that we can recognize in some form when we think of GR. So.
You mean how can you apply the scattering amplitude method for non-perturbative things? That's like
even in the perturbative case, what is it that we're really? What are these observables in gauge invariant? Maybe this is the part that is related to the fact that it's Postman-Pasquian and not Newtonian. Because in the case of the gravity waves, the standard calculations, it looks very gauge dependent. It looks very.
I mean, you compute the deflection angle. This is a gauge invariant expression, and you can compute to any order of perturbation theory. It's no problem. The zero frequency limit of the spectrum is a gauge invariant quantity. It's a classical you compute.
And okay, then the next, which is that in the non-perturbative regime, what would the equivalent of diffeomorphism invariant observables be? That's also sort of the class of things that we would like to be able to reproduce in any fully quantum theory. So.
We still use the amplitudes of the formalism
Generally,
to check the UV part.
So without using perturbative.
I mean, you cannot use the perturbation theory, then you have to use your own theory in your UV language to extract the UV part of the amplitude.
Okay, more questions? Yeah, yeah.
Corrections that you get. I understand that the Bible square that you get somehow is expected because we have some tensor structure which is similar to the area metric, more or less. But would you also expect some R square term coming out from I don't know where?
Well, maybe from other effects, but otherwise, yeah, it's well, you do get the Weil squared because the chi's they are spin 2, and they couple to only to the spin 2 part of the H metric of the length metric, and so that gives you just the Weil part squared. Well, but definitely, I think definitely I don't see this R squared part like from area Ricci calculus. So, and I think if it would be there, I would see it at this order. Yeah, it would, or the fourth, it would be fourth order in derivatives. So, well, there might be something going on with, if you are on a lattice, you have the lattice momenta, which are exponentiated, exponential ik lambda with some lattice or divided by lambda, whatever. And so you get always higher order terms, even just from length Ricci. And these are kind of not obvious to interpret. In particular, like seeing that, in this case, seeing that this was something like Weil squared. Well, in the squared formulation, you would never see it, but I saw it that the terms you get to the Weil squared was a Weil curvature. But you have to guess that, it's not kind of, I mean, you have to recognize the components of the Weil squared thing. So there could be something from these higher order terms, which more or less come only from the expansion of the kind of exponentiate momenta. And but so far I kind of treated them as lattice artifacts. But maybe there's something also physical behind not having an R squared.
Yep.
Can I follow up on your question? So, in the non-perturbative case, is it when you calculate these things, are you still going to use, are you going to use a fully Lorentzian framework to do these calculations? In which case, I mean, that becomes important, right? I mean, you can do things about flat space-time and you can get away with Euclidean techniques to do that. But when you're calculating these things in a non-perturbative way, you're doing these amplitude calculations. And you're trying to construct observables for Lorentzian theory. I just want to know, what is the status of these non-perturbative calculations? Because that's where you'll hit that's where you'll hit the issue, right? I mean, and this is what I think we're trying to do in sort of more sort of whatever, however you call it, top down or bottom up approaches to quantum gravity, where you're trying to really intrinsically define things in observables, like what Bianca's talking about. So I'm just curious whether these things, which, I mean, it may be that you capture a certain class of interesting observables, and surely for scattering theory and stuff like that, things that I have to make in the deep quantum regime with these. Do you think that these would be relevant? And if so, how would you get over this Euclidean Lorentzian barrier?
Of course, these approaches depend on the difficulty. That's why we address this issue in a way to functional methods with functional normalization. Typically, we use Euclidean computation, and then ideally through computation after we differentiate back. But now there are also new technologies to do the calculation in Lorentzian flow. Maybe Jan can tell you better about that. And the other approaches, of course, we have different ways.
I will say something in my talk.
But everyone can look at the talk on the YouTube after.
Thank you.
Well, I would like to make a general comment in relation to your question. I think here we talk about quantum gravity as if it was just one thing, but apparently people have very different ideas of what it is. And there are people who want to compute things that like scattering amplitudes or scattering angles, for example. And then the methods that they have work very well, and they are perturbative methods. And they have to assume that there is a space-time to begin with. Now, people who do non-perturbative things, instead, I think that the main thing they want to explain is, first of all, why there is a space-time. And that's a much more basic question. You are starting from way, way further back. And so to imagine that starting from so far back, you can compute the scattering angles, I think it's unrealistic. And I think this is what Renata has been saying several times.
I agree completely. So
yeah, and so
yeah, but the question is, when you talk about these observables as potentially being useful for quantum gravity, that's where I'm coming. I mean, I'm asking, how can that be? Maybe I'm asking it a bit too politely, but yet I'm asking, how can that be? Because it feels like one is coming from the perturbative calculation, and then to get to anything that's, you know, fundamentally quantum gravity is a big, long thing.
But why do you say fundamentally quantum gravity? I think when you do quantum theory of gravity on flat space is quantum gravity. Why don't you want to call it quantum gravity?
Non-perturbative quantum gravity. Okay, so maybe.
Okay, but then if you have, once you have a theory that explains flat space and perturbations around flat space, for that theory to be good, it has to match the results that are obtained from in this way.
Why is it not true?
Because you would precisely, because you're doing things about that.
But that does not mean it's just.
Flat space-time could be a solution of, or could correspond to a state of the non-perturbative theory, as well as, you know, excitations about it that look like gravitons. Could certainly be, you know, states that are exact states in the non-perturbative theory.
So what I want to say is that for a non-perturbative theory to be acceptable, it has to match the results of the perturbative theory.
I think.
Anyway, maybe
Perturbative, I mean, standing around flat space, and you have random scattering.
anyway,
There's a geometric expansion in that sense.
to answer Sumati's question, there is well, at least I defined observables, which you can then evaluate perturbatively, and to lowest order you get graviton observables. But yeah, in principle you can extend them to fully gauge invariant observables. So yeah, scattering amplitudes in principle you can define them non-perturbatively. You have to assume asymptotically flat boundary conditions, and so that's something like a classical regime, which you might not be a big fan of, but so you can formulate that assuming these kind of asymptotically flat boundary conditions.
Do we agree?
No, of course, we don't agree.
Me and you don't agree.
Yeah, anyway. I would call an effect in quantum gravity, even in flat space, which has something like exponential of -1/Newton constant, a truly non-perturbative effect. So I understand what you mean with an expansion about flat space being a perturbation. We single out a background, but we want to, in most cases, talk about quantum gravity, which sums over all geometries. But having one expansion around does not make the whole thing perturbed. So I'm a bit lost at this definition. So an expansion is expansion, yes, but it does not make the whole thing perturbative.
I'm not saying that the whole thing is perturbative. I'm saying that there's a concrete calculation done by Paolo, where it computes some scattering angle. Is this perturbative or not?
This is a perturbative
Please,
computation.
Paolo, say, is it or not?
No, this is a perturbative computation.
Yeah, so I'm talking just about that.
There was a question and it was addressed to Bianca, not about
But just in connection with that, you could imagine if Paolo were infinitely more powerful, that he could calculate, or maybe with some other methods could calculate non-perturbative corrections as well to these amplitudes. And in fact, there may be sort of semi-classical methods to at least estimate those amplitudes and find that kind of behavior that you're describing.
Which still would be in flat space.
Well, yeah, they would correspond to, corrections to amplitudes for scattering of perturbations about flat space, but you could have non-perturbative corrections to those amplitudes. Yeah, okay, good. At least some of them. Maybe.
Yeah, I mean, I just wanted to point out what Ivan said, that in very simple, idealized, unrealistic cases, there are explicit examples of these effects that can be computed. Even examples.
So for example, you can do what kind of non-perturbative observable would you do?
For example, again, very idealized settings that were studied in the 90s, for example, a particular piece of the amplitude, a particular coefficient in the low energy expansion is a certain type of Eisenstein series that has, if you expand it in these transperturbative series, you get this instanton-like contributions, but the full result is given as a certain Eisenstein series that has certain modular property. Complicated, but the point is that the expression is known in these particular idealized.
You have also expansion in terms of gravitational instantons, and that's to get these effects.
Absolutely.
Even though this again is an expansion about.
I would call it so at low energies at least at low energies when the couplings of gravitons are small, I would call this a transperturbative theory. You have the trivial saddle and the instantons with each their own asymptotic theories are about the atom.
Okay, so there seems to be some agreement now. More questions? Yeah. Yes.
So there's agreement and not lack of understanding. I don't quite understand what these answers mean. So.
Give time to discuss it more. More questions or follow-ups? Yeah.
At some point we discussed a little bit about these amplitudes, and you mentioned that at least some, if I remember correctly, discussion can be computed in principle using stringy methods, just as functions of alpha prime, and then taking the limit where I guess the string length goes to 0. Was that also included in the things that you have said in your talk?
Some of the calculations.
Okay, and they still do match the amplitude compute using perturbative methods in general relativity.
I mean, I will discuss that in the panel discussion. Let me say. Sorry. I mean, if you want to compute an amplitude with many gravitons in field theory, you have a lot of Feynman diagram, as you know. In string theory, for instance, the 5-point amplitude with one graviton, to compute the expression is complicated with all the Feynman diagram. So for me, it's easier to compute the amplitude in string theory and then go to alpha prime going to 0 limit and get the field theory result. Of course, the field theory result is obtained also from the Feynman diagram. It's just a question of avoiding the 3 graviton vertex that comes out or automatically in the amplitude.
So in a sense, in that case, you're using the string theory as a sort of a regularization of field theory, at least in the limit to what is like the large distance limit.
Yeah.
It was super clear from the talk that you were using this technique, at least for me. I don't know if I missed something. And if can a question but staying in the subject of gravitational waves, but to Bianca. So you expect, since you have this additional degrees of freedom that are of gravitational origin, that they could affect the spectrum of gravitational waves. And I'm asking this question for a specific reason. So there was a paper by Javier Calmet some years ago, where he was considering so a completely different system. So he had just quadratic gravity with root corrections, truncated to quadratic order. So there were also 2 additional degrees of freedom on top of the graviton that have the spin 0 scalar for the scalar and the ghost. And with that, he was concluding that there are corrections to the gravitational wave spectrum that are induced by these additional degrees of freedom. So I was wondering if you would expect that the additions.
So I'm not quite sure what you mean with spectrum. In the linearized calculation, where we go to the Hamiltonian picture, where you basically diagonalize evolution matrix, and there the graviton. Well, there's a massless degree of freedom, which is a graviton. And you get these additional, 2, or actually 1, because you can redefine, in this case of special symmetry, it's only 1 massive spin 2. So it's Planck mass, so maybe you could say that as an additional degree of freedom. The effect you get from this extension, well, it has something to do with this parity violation. So that is not, I wouldn't say it's a spectrum. But if you look at the evolution, we get a mixing between the plus and cross polarization. And that does not happen in pure gravity. And this mixing depends on the value of the Barberio-Misi parameter. If somebody can tell me how to measure it, I would be interested. So that would, well, that might be a possible sign of this extension. Also, I guess if this Barberio-Misi parameter, if it's not parity violating, you might not get it. I should check. So it does influence. It does influence the propagation of gravitational waves via this massive spin 2 channel. And you have an additional spin 2 particle, or 2, depending on whether you are at the special value of the coupling or not.
Just getting back to the previous point to clarify a little bit what people mean when they talk about non-perturbative versus perturbative. Of cutting things short, as was just pointed out, and glossing over issues that obviously you can have an essentially kind of perturbative formulation, by which I mean you're working just with linearized configuration spaces, and you can obviously have these symptomatic effects, and no one can deny this. But I would say these are non-perturbative elements that can, change some of the results, and maybe even influence them in a drastic way if you have an infinity of such contributions. That's certainly fine, and you can call that, well, you can say that's not just perturbative, and that's fine. It's just a question of what one calls it. When people like myself doing that, talk about non-perturbative rate, it does mean taking the nonlinear structure of the physical configuration space seriously and going beyond, just quadratic, doing Gaussian, just standard perturbation theory, probably enhanced by non-perturbative elements. As a non-perturbative elements could also be something like a weak, strong coupling duality, where you then get back maybe from some weak coupling regime that enables you to make some statements. So you could also say, well, that's then a non-perturbative formulation, and that's perfectly fine.
I use the instantons as an example that everybody knows about.
Yeah, for sure.
So the non-perturbative, you have an expansion for that space, also concerns the standard non-perturbative effects on the lattice. What it does not include is, of course, the geometric expansion, like there are different geometries.
Yeah. So there is also no background to start with. That's right. Background independent. Background. Yeah, that's different.
At least, that's what I mean. Non-background.
But I don't think that's perfectly fine from how we're doing these computations and just getting information about classical GR in your case. I mean, that's perfectly. Yeah, it's going to be fine. I mean, you were not claiming that, you were even trying to reproduce what John has done, and that not being exactly easy technically, let alone, full non-perturbative, orders of H bar. Some, but there are no contradictions there, but one should be slightly careful in what one means by, these expressions, perturbative, non-perturbative. Maybe it's good to add the background independent. Yeah, maybe you can also manifestly background independent, right? Yeah. No. No, but this has a well-defined meaning. Sorry, right? I mean, of course, I can put in a background, and then I have a rigorous proof that nothing depends on that choice. I think that for me would be fine.
Well, look, I mean, in effective action, we are computing operator coefficients like the Wilson coefficient. And choosing a background is a means of computation. It does not mean we fix your background. It means
not necessarily. That's what I'm saying.
It means it's just a projection method. And then having the distinction between manifestly background and not, it's a bit meaningless.
Well,
so I'm not saying that I understand where these conditions come.
In gravity? In gravity?
I'm just saying that if I want to compute an operator coefficient like the Wilson coefficient, and I have something like the RG equation,
but I
need a projection method.
You're taking gauge theory.
Yes.
Yeah. I'm talking gravity.
I'm talking about gravity. Gravity is a gauge theory.
No, it's not. It's not the same thing. I would disagree there.
Yeah.
It's not the case.
It's not the case. But okay,
But anyway.
I don't think we disagree in a very, I'm just trying to, what would be good ways of talking about these things that can be least misunderstood.
Yeah, but we again have something in terms of the effective action and in terms of projection. It's a gauge theory because we have symmetry constraints, and for computational purposes, that's all. I understand why you disagree with it, but that's again the question: how you, if you wish, get your results, after risk coefficients, I have to take into account the gauge nature of hypnotism invariance. I'm not interested in the way that there's not. I just want to compute these. So and there these distinctions just don't make sense. I'm not saying I know why why you use them and that they make sense, but they don't make sense in all the methods we have.
Well, I would say in verities there are additional subtleties that come exactly from the need to be generally diffeomorphism.
Oh, I understand this.
Good.
I mean, and also, just a bit about, when you say that instantons contribute, right, so that's a non-perturbative contribution to things that you're calculating as expansions about flat space or something. You find these extra contributions, but in terms of observables, and that was sort of my first class set of questions, are these observables to do with these particular low energy scattering things, or because then gravity, when how do you define observables, get diffeomorphism and various things? These are big questions, and we don't really know and so because you're talking about some class of observables, I wanted to ask, what are the class of observables for the background independent observables? Maybe that's the way to phrase it. So I shouldn't say non-perturbative, but background independent class of observables. Do you think that these amplitudes could give you things that are background independent? I won't even use the word manifest.
If I may, I think there's a little bit of a semantic mix-up here. And, that is, there are observables that are things that we can observe or measure, and might think in some sense the S matrix is an observable in that sense of the word. The S matrix is something we sort of do measure at, places like CERN and so on. And then there are the quantum operators that are the, quantum observables in the theory. And those are, technically that's not the same thing. Those are things, we say matrix elements we could compute, and then we might identify with those the things that we can observe. So they're different notions, and so I think we should maybe keep track of those. And so, for example, coming back to the S matrix, that's something that it's been described how to compute order by order, and presumably in a nice gauge of weight fashion, et cetera, et cetera. But that's distinct from the question of defining the observable operators. They're the things that we want.
So and then classically, I mean even classically asking the things that are in the without doing perturbations in the fully background independent way can be described here. But okay, so maybe can postpone this to later. I feel like I'm just saying the same thing.
Yeah, it's a really interesting discussion, but we are also running out of time, and I think we've stressed our speakers enough. So let's thank 2 speakers again.
Like it was like